Hey, hello, welcome. Let's try to solve another Leetcode problem, 1215, stepping numbers. So the problem is that we are given a low and high, and we just want to find all the numbers, which is more than equal to low, less than equal to high, but all those numbers should be a stepping number. So the definition of the stepping number is like 3 to 1. So the step of each of the number, the difference of the neighboring numbers is going to be 1. So this is going to be the definition. So if we understand what is the stepping number, and according to this low and high, definitely we can solve the problem. So let's just check the low and high. So it's going to be maximum 2 to the power of 9. So this means we cannot solve it by using the brute force, because the brute force idea is that we're going to try to check all the numbers one by one. So it's going to be like 2 times 10 to the power of 9 on different numbers. And for each of the number, we're going to check the length of the number. It's going to be another 10 maybe. So this is going to be the time complexity. Of course, this cannot pass. So another idea is that according to the definition of the stepping number, so for example, if we have a number like 12, so what's going to be the next number? Because according to the stepping number idea, so the next number can be 1 to 1. Yeah, so the next number 1 is less than 2, and the absolute of 2 minus 1 is 1, and maybe we're going to have 1, 2, 3. Yeah. So let's just continue. Maybe 1, 2, 3, what's going to be the next? So it can be 1 to 0. I'm sorry. Let me just 1 to 1, 0. So this is going to be a stepping number. And another one, it can be 1 to 1, 2. Yeah. So this seems we can solve this problem by using the search. So the search is going to be a DFS or BFS. Definitely we can solve the problem. And also we need to analyze the time complexity before solving the problem. Otherwise, how should we know it's going to have time limit exceeded? So as the maximum of high can be 10 to the power of 9. Yeah, let's just imagine it's going to be 10 to the power of 9, this number. And this is going to be a binary tree. And we need to know the depth of the binary tree. So according to this kind of idea, the depth of the binary tree, actually, it should be log 10 with 10 to the power of 9. Yeah. Actually, it is 2 times 10 to the power of 9. It is log 10, 2 times 10 to the power of 9, because this is going to be the depth of the tree. And this one, basically, this number is going to be 9. As this is a binary tree, and the depth is 9, so basically it is like 1 plus 2 plus something plus 2 to the power of 9. So the final time complexity is going to be 2 to the power of 10 minus 1. Yeah. So this means if we use the BFS or DFS, definitely we can solve the problem. It's going to be 2 to the power of 10 minus 1. This is going to be the time complexity. Basically, it is 1024 minus 1. And it is 1023, basically like 1000, so the time complexity is okay for such problem. Yeah, and the space complexity, it is dependent on the array, so it is also 1000. Yeah, so it seems we can solve this problem by using the BFS or DFS, but I prefer to solve this problem using the BFS. So we're going to prepare a result, and we're going to return the final result. And first of all, we're going to check this low, because we need to consider it separately, because there's no such numbers like 0, 1 or 0, 1, 2. We don't have such kind of numbers, so it means there's no leading zeros for such numbers. So we're going to consider it separately. Yeah. So for the BFS, we're going to just put the numbers like 1 to 9 inside the queue. And then we're gonna start the BFS search. So if this number is more than our the high, we're gonna stop it. If it is more than low and less than or equal to high, we're gonna put it inside the result array. So this is gonna be the BFS. Yeah. Now we're gonna check it separately. So if it's low equal to 0, and we can directly put it inside the result array, and it's gonna be okay. We just put yeah, we just put 0 inside the result array. Now we're gonna start the BFS, and we're gonna start the BFS. So first of all, we're gonna prepare a double-added queue, and the value gonna be I from 1 to 9 for I in range. Yeah, maybe we can use another way. Maybe we have different ways to write this. So it from 1 to 10. So basically, we're gonna have an array. So this array is from 1 to 9, and from 1 to 9, we're gonna search. We're gonna use the BFS to search it. Yeah. So while q, we're gonna pop out this value, and it's gonna be q.pop left. Yeah. So according to our design, so the popped value gonna become bigger and bigger. So first of all, for example, we're gonna pop out 1 and then 2 and until to 9. So the value gonna be bigger and bigger. So this means we can check it directly. So if this value is more than high, we can stop it directly. This means we're gonna return the result. Yeah. So finally, we don't need to return this result because we can check it from here. So otherwise, if this n is less than and if this n is more than and equal to low, definitely it's going to be less than equal to high because here we have a tag. Yeah. So if there's no return, definitely we're going to tag this number if it is more than equal to low, and we're going to put it inside the result array. Yeah. And we're going to put this number inside of the result array. Yeah. And the next step, we can start the BFS part. So first of all, let's just prepare a last digit, because this is important for our calculation. So the last digit is going to be n modulo 10. So for example, if this n is 1 and 1 modulo 10, it's going to be 1. Yeah. And the next step is that we're going to check in which condition we're going to put it inside the queue. Yeah. So we're going to check this last digit. So this is a very important information. So if the last digit is from 1 to it's more than 0 and less than 9, basically for our tree. Yeah, so for our tree, if like it is 1, it has 2 branches. So for example, the next number can be 1 0 or it can be 1 2. Yeah. But what about the last digit that is 0? So currently, because we put the 0 inside the result, it is not inside the queue. But for example, if it is a 10, so what's going to be the next number? We only have 1 branch. Because the last digit is 0, we cannot have 1 9, but what we can have is that we're gonna have like 1 1, 11. Yeah. So this is one condition, and another condition is that what about the last digit is 9? So that means we can have 8, but we cannot have 10 because this didn't meet the condition. Yeah. So there are only 2 special cases, and we have to check it separately. And except that, we're going to use 2 branches. And if it is 0, there's 1 branch. If there's 9, there's only 1 branch. So if it is 1 to 9, we have 2 branches. So this is going to be the BFS. Yeah. So from here, we're going to have a tag. So if it is this last digit is more than 0, so definitely this means the last digit is not 0, right? So for our queue, we're going to append the number which going to be the current number times 10. Yeah, because we need to add 1 digit, and the digit going to be the last digit minus 1. So this is one condition. So another condition is we have to use another if. Yeah, because I don't want to write all the conditions together. I just want to use 2 if conditions to combine all them together. Otherwise, I have to prepare a lot of if-else check. Yeah. Another condition is if the last digit is less than 9. So Q need to append n times 10 plus the last digit plus 1. Yeah, because only those two lines actually include all 3 different combinations. Yeah, so let's check it one by one. So if this number is like from 1 to 9 included, so here we have a branch, because 1 minus 1 it is okay. Here we have another branch, 1 plus 1 is okay. Yeah. So if this number is 0, it goes to here. It means it's going to be a 0 plus 1 for the last digit. And if this number is 9, it goes from here. It means the last digit going to be 9 minus 1. It's going to be 8. Yeah. And in this kind of design, because we just append the queue one by one, and this is smaller than this one, than the last one. It means inside the queue, if we populate from the left side, all the numbers will be in increasing order. So this is why we can check it from here. Because all the numbers is in increasing numbers, the number going to become bigger and bigger. So if we find a number that is more than high, so we can stop it immediately. So we're going to return the result. So I think everything should be okay. Now let me just run it to check. As you can see, it works. Now let me just submit it. As you can see, it passed all testing cases, and it's pretty fast because the time complexity, as I explained earlier, it is log 10, 2 times 10 to the power of 9, and basically this is a 9, and then we're going to use 1 plus 2 plus 2 to the power of 9. It is a 2 to the power of 10 minus 1. Basically this is going to be the time complexity. It is around 1000, and also for the space complexity, it is also 1000. Because we just put the numbers inside, there are going to be 1000 numbers maximally. Now let's just do some change. Maybe you just forget about it. You don't know we need to keep the numbers in increasing order inside of the queue. If you did it like this, definitely it didn't work, because this is not how we designed the algorithm. We needed to keep all the numbers inside of the queue to be in increasing order. If it is not in increasing order like this kind of way, definitely it will not work, but let's just have a try. As you can see, it didn't work. So every step matters, and it is always according to our design of the algorithm. This is why we're going to check it from here, and this is why we're going to check the low. Now let me just submit it. So I think that's all for it. Thank you for watching. See you next time.